Hello and welcome back to Zig's Math Lessons. Let's review what we did on the first half of this lesson, discuss it a bit. This is a horizontal compression of y equals f of x. Horizontal because the factor 5 is within the input station. Anything within the input station has to do with horizontal motion. So the question is, how is this a compression? Wouldn't it be a stretch? It's a pretty natural question. I mean, it says 5 times. Wouldn't it be a stretch? No, it turns out to be a compression because the 5 is operating on the graph paper. It's the graph paper itself that gets stretched by a factor of 5. So if you can envision what happens to the function itself in relation to the graph paper, it appears to shrink horizontally, that is. So it's a horizontal compression because it's within the input station, and it's a compression because this number is bigger than the number 1. And what we do is we take all the x values and divide them by 5. And the result is a horizontal compression. Here's a horizontal stretch. These are all the same. They're identical. Some people write it as x over 3. Some people write it as 1/3 x. Either way, when you take the x values and divide them by 1/3, that's like multiplying by 3. Hence, it's a stretch. And it's horizontal because it's within the input station. This is a vertical compression because the factor is less than the number 1. And this will multiply the y values, hence it's vertical, because it's multiplying y values, as opposed to this, which divides x values. This one multiplies y values. 0.75 is the same as 3/4, and 3/4 f of x is the same as 3 times f of x over 4. I wrote them all the different ways that different people write them. These mean the same. And it's a vertical because it's outside the input station, and it's a compression because we're multiplying by a number less than 1, as opposed to a vertical stretch where we multiply the y values by a number bigger than 1. So these multiply y values. These divide x values. Reviewing back further, this is a shift to the right too. You see the minus sign? The function goes to the right. And the reason is because the graph paper actually goes to the left too, but we can set that aside and just understand that if you see x minus 2 at the input station, the function itself is shifting to the right. Here's a function that shifts to the left 3 and then gets horizontally stretched. I can see it shifting to the left 3 because of the plus 3 within the input station. And we have a b value here which divides the x values. And when you divide by 1/2, you're actually multiplying by 2. So hence it's horizontal because it's in the input station. And it's a stretch because it's a number less than 1. This is a vertical compression with a right shift. We can see the right shift here within the input station. Anything in the input station is left-right motion. And we can see this is outside the input station, so it's vertical, and it's a number less than 1, so we're going to multiply the y values by a number less than 1, and that's going to cause a vertical compression with a right shift. Here we have a vertical stretch and a shift down. Vertical stretch because it's 7 times a y value, not within the input station, so this is vertical motion, and it's multiplying the y values, as opposed to this 1/2, which divides x values. This multiplies y values, and then take the whole business and shift it down 3. Hence, vertical stretch and shift down 3. We need to be totally used to what we've been doing lately in math class with functions. Let's proceed to today. We'll do reflections. Here's a picture out the back door of where I live. And you can see that the lake is very quiet because it's 10 o'clock in the morning on on a Sunday in early September. The lake is quiet. Where's my neighbor down there? He's got a little float plane. He takes it off across this lake. It's quite a nice little spot. Now, let's take a look at this. What we see in the lake is a reflection of what's on the shore. You can see the reflection here. If I impose a grid on this photograph, I can see that it's a reflection across the x-axis, because what's above the x-axis is reflected below the x-axis. For example, if there was a bird 5 meters above the ground in that tree, right there where the pointer is, its reflection would be 5 meters below the shore in the reflection. So when the y value of the bird in the tree was 5, the y value of the reflection is -5. So when y gets replaced with minus y, it's a reflection in the x-axis. And let's also pretend that there's a groundhog right here at the shoreline taking a drink. The groundhog is touching his own reflection. So that's just an important note that we'll refer back to. This is a reflection in the x-axis. This is a reflection in the y-axis, because look at this dog's collar. Suppose that x value for the edge of that collar was 7. X value of 7 at the dog's collar. In the reflection across the y-axis, the x value of that dog's collar right here on the edge of it would be -7. So when x got replaced with -x, it's a reflection across the y-axis. And this is what you have to get. Reflect in the y-axis, x gets replaced with -x. We have a reflection in the y-axis. This is the concept. Formalizing it, reflections of functions. Y equals -f of x is a reflection of y equals f of x. In other words, y got replaced with -y, reflecting the x-axis. Always with the paradoxes. That replaced with that, reflect about the x-axis. Y gets replaced with -y. This is pretty clearly x has been replaced with -x. X has been replaced with -x. So it's a reflection about the y-axis. Always with the paradox. Replace x with -x, reflecting the y-axis. Replace y with -y, reflecting the x-axis. And the groundhog, that's called an invariant point. Invariant points are points that remain unchanged. The groundhog was touching his own reflection, so in the reflection, that point would stay unmoved. Invariant. Okay, let's do some algebra with this. Given an equation, state the equation of the reflection in the x-axis. So you have to have it down pat. You reflect in the x-axis, replace y with -y. First we'll copy the question, and then replace y with -y, quite literally. And then simplify it to y, so we'll multiply both sides of this equation by -1. And we have this. This is the reflection about the x-axis. Y got replaced with -y, and you might notice that each sign on each term got changed. I just took out the middle, take out the middle intermediary step to look at the original and the result. You can see that in the result, x squared became -x squared, plus 3x became -3x, -2 became +2. So if all the signs on all the terms get changed in a polynomial, it's a reflection in the x-axis, because y gets replaced with -y. Let's reflect it across the y-axis. So we have to know that means to replace x with -x. First copy it, and literally replace x with -x. You'll need brackets for that. Now when you square a negative, it turns back positive. But when you multiply this out, you just get -3x. So here we have it. Done. Reflection in the y-axis. Given a function, different one, state the coordinates of the invariant points, the groundhogs, if you will. under the two transformations. So let's try f of minus x. Well, x got replaced with negative x. This is what you say to yourself. X got replaced with negative x. So it's a reflection across the y-axis. Now in this transformation, points along the y-axis will be invariant. That's going to be the y-intercept along the y-axis. So we need the y-intercept of this function. You learned in grade 9 that mx plus b, the b value, was the y-intercept. Well, it also works for parabolas. In fact, all polynomials, the constant term on the end is the y-intercept. So the y-intercept here would be 0 minus 12. And that's invariant under this transformation because it's a reflection across the y-axis, because x got replaced with negative x. Here we have y being replaced with negative y. So we think y replaced with negative y, that's a reflection in the x-axis. That's the birds and the groundhogs picture. So points along the x-axis, like the groundhog, will be invariant. Points along the x-axis will be invariant for this transformation. These will be the x-intercepts. Because y got replaced with negative y, it's a reflection across the x-axis. We want the x-intercepts. They'll be invariant. X-intercepts. Well, go back to grade 10 and remember, how do you do that again? How do you find the x-intercepts of a parabola? That's right. You set it equal to 0 and factor. Good job. Okay. Okay, so here we have it. I set it equal to 0. I factored it. And we need x equals 4 or x equals minus 3. So 4, 0 or minus 3, 0. Invariant points under that transformation. Let's do some graphing. Given a function, y equals f of x. Kind of looks like the Big Dipper. Not really, but kind of. Given a function f of x, graph f of minus x. Think to yourself, x got replaced with negative x, so reflect across the y-axis. Take this corner point, reflect it across the y-axis. Take this corner point, reflect it across the y-axis. It's 3 to the right, make it 3 to the left. Take this corner point, reflect across the y-axis. It's 5 to the right, make it 5 to the left. It's really pretty simple. Take that corner point, reflect it across the y-axis. Well, it's over here at 6 on the right, so we got to move it all the way over to here to 6 on the left. Play connect the dots and label your graph. Y equals f of minus x. X gets replaced with minus x, reflect across the y-axis. Let's do another one. Given a function y equals f of x, graph y equals negative f of x. So here's y equals f of x, and we want to graph y equals negative f of x. So y, which is f of x, got replaced with negative y. Y replaced with negative y, reflect across the x-axis. Always the paradox. So we got this point, which is 3 above the x-axis, so we'll make it this point, which is 3 below the x-axis. This point, which is 1 below the x-axis, has to reflect across the x-axis, so it's 1 above the x-axis. Same with this point. It's 1 below, make it 1 above. This point, which is 1 above, has to reflect across the x-axis, so we'll take it and push it down here below the x-axis, 1 below. Play connect the dots, label your graph. Notice the invariant points. This is where the two graphs intersect. This is where the groundhog is taking his drink right here, sitting on his own reflection. The invariant points will be found along the x-axis if you're reflecting across the x-axis. State the equations. All right, here we go. The parent function looks like the top half of a parabola. So our parent function, the top half of a parabola that opens to the right. This is what the parent looks like. But we want it shaped like this, opening this way. So it seems it's been reflected across the y-axis, so we'll have to replace x with negative x. The parent function reflected across the y-axis. Let's do it again. Looks like the bottom half of a parabola. Okay, so the parent must be the bottom half of a parabola. Good thing you learned the parent functions. This is the bottom half of a parabola. Now we need it shaped like this. So this one isn't shaped right. So we have to flip it across the y-axis. This is the y-axis. Flip it across, and it'll at least be shaped right. So let's do that. Now, how are you going to reflect it across the y-axis? Replace x with negative x. Like that. Now it's at least shaped right. It's kind of shaped like this. And now we have to take this and shift it to the left 3 up 2. Now, left 3 means right at the input station, go x plus 3. The brackets are necessary because it has to be a positive 1x there. And then outside, plus 2 will shift it up 2. Label your graph. Now let's consider this point minus 7, 0. Because as a math student, you really should be skeptical. I mean, here's some teacher saying, well, the equation of this is y equals negative root negative x plus 3 plus 2. And you're supposed to just buy that? Well, no, you should be skeptical and say, okay, wait a second. I wonder if this point works. There's a point right there. I wonder if it works. So plug in minus 7 for x and see if you indeed get 0 for y. So minus 7 for x plus 3 is minus 4. Negative minus 4 is 4. Root 4 is 2. Negative 2 plus 2 is in fact 0, so it works. State the equation. Looks like the bottom half of a parabola. There's the parent function. Now, it's been stretched. There's the parent function, but it's been stretched. So we'll put an a there, and we got to figure out a. And we remember that a is actual over expected. So consider this point here, 1 minus 3. We expected, when we displaced ourselves 1 from the vertex, we expected to go down root 1, because it is, after all, a root function. But that's not actually what we did. We actually went down all the way to there, which is 3 down. So actual was 3 down, when expected was 1 down. So actual expected is 3 over 1, which is 3. So the a value is 3. And we can now state the equation of our graph. And as skeptics, we're going to test a point. I wonder if this point works. Okay. Well, if I subbed in 4 for x, I'd get root 4, which is 2, and negative 3 times 2 is negative 6. And yeah, that's the y value, so good. That one works. Moving on, state the equation. Top half of a parabola. There's the parent function. Top half of a parabola. Got to get it shaped right. So flip it across the y-axis. So make x negative. Replace x with negative x. And now it looks like this because it got reflected across the y-axis. And now you simply have to shift it left 2. Right in there, inside of the input station, we have to shift left 2. Will that be plus 2 or minus 2? Well, it's the opposite of what you'd expect. Left, I would think minus, so go plus. There it is. Now we can test a point if you'd like. Let's go to minus 3, 1. If I sub in minus 3 for x, I should get 1. Let's sub in minus 3 for x. Minus 3 plus 2 is minus 1. Minus 1 is 1. And root 1 is 1. So if I subbed in minus 3 for x, I do in fact get 1. So that point works. Here we go again. Parent function, bottom half of a parabola. From our parent function knowledge, flip it across the y-axis, because this is the parent function. The bottom half of a parabola has to be flipped across that y-axis. So replace x with negative x. Now it at least is shaped right. Now it needs to be shifted to the right 3 and up 5. Okay. To the right 3 means right in the input station with x. Shift it right 3. That shifts it right 3, and then outside the root sign we have a plus 5 to shift it up 5. Testing the point minus 1, 3. There it is, minus 1, 3. Plugging in minus 1 for x. There's minus 1 for x, plugged in using brackets. Working here, minus 4, and minus 4 is 4, so this is negative root 4 plus 5. Root 4 is 2, and negative 2 plus 5 is 3, so we can say f of minus 1 is 3, as desired, because minus 1, 3 is this point right here. Just testing a point to see if we got it right. Identify the transformation that maps this onto this. We see that. We look and we dwell for a moment. The plus 3, it's still plus 3. 2x became minus 2x, so we replaced x with negative x. To go from f of x to g of x, we replaced x with negative x. That's a reflection across the y-axis. A B question. It's a polynomial onto g of x, which is, a similar polynomial. Minus 3x has become positive 3x. X squared has become minus x squared. We notice that the signs on all of the terms in a polynomial expression have changed. So y must have been replaced with negative y. And so this is a reflection in the x-axis. I'm not Siegel, be it be stunt, but thanks for watching, and if you liked it, leave a like, and if you like the content, then please subscribe and ask any questions that you might have in the comment section.